everyone, welcome to Engineer's House channel. Today's video is about fatigue failure. If you are a mechanical engineering student, you've probably heard about fatigue failure. In fact, fatigue failure is a predominant type of failure in many engineering and construction applications. It is frequently seen that machine members are found to have failed under the action of repeated or fluctuating stresses, even though they haven't reached their ultimate strengths or even their yield strengths. This type of failure that occurs due to these repetitive cycles on the long time is called fatigue failure. In today's video, we'll focus on completely reversed cycles. But what do I exactly mean by completely reversed? Imagine a rotating shaft that is subjected to a constant bending load, and it rotates with a specific velocity. As the shaft rotates, the magnitude of stress varies between tension and compression. As you remember from statics, compression is negative, but tension is positive. So as long as you're moving between these two equal but opposite magnitudes, you have a zero average. Having a zero average will lead you to completely reverse stress cycle. Clearly, to establish the fatigue strengths of materials, a number of tests are performed. However, the most popular one is known as rotating test beam, in which a constant bending load is applied and the number of revolutions required for fatigue is recorded. Eventually, all the results are plotted as an SN diagram with a logarithmic scale. This is the diagram I just mentioned. And there are a few things you need to know about this diagram. First of all, the y-axis is the fatigue strength that is denoted with SF. On the other hand, the x-axis is the number of stress cycles. Keep in mind that fatigue strength is basically the stress under fatigue loads. These diagrams has important information inside it. First of all, this fragmentary line tells us a lot about fatigue failure. If your design component is under this line, it means that you are in the safe area. But passing this line will cause you some problems. Your component will be totally unsafe, and within any cycle it will fail. Sometimes not even statically, but in a fatigue way. There are some parameters you need to know in this diagram. The first is SUT. As you remember from statics or the mechanics of materials, SUT is the ultimate tensile strength that is obtained from the simple tensile test. This parameter is unique for each material. The other factor is F times SUT. SUT is what we just mentioned, but F is another factor that we will discuss later. For now, you have to know another factor that is SE, or the endurance limit. The endurance limit is an essential parameter that needs to be considered in many designing problems. It is quite important to know what effect this parameter has on our components. For values below this line, your machine component will have an infinite lifetime. But if you exceed this limit, you will be within this area, which is not an infinite lifetime, but a finite one. Having a finite lifetime has some problems, and it could be a little problematic to some designing issues, since being in this area means that you cannot use your components permanently. But having an infinite lifetime is a perfect thing for engineers. The other things that you should know are low cycle and high cycle. By low cycle, we mean that the number of cycles that has happened in a process or in the life of a machine are within this area, are from 0 till this number. But if your process is a high cycle one, you are in this area. Being in this area has some better applications, but for now, the only difference between low cycle and high cycle is being in this area or this area. Okay, so let's know more about the endurance limit, which is an essential parameter in all designing problems, and that is every material has its own endurance limit. So it doesn't mean that steel has the same as iron or the other ones. But since we are mechanical engineers, we care about steel the most. We use steel more than other parameters, more than other materials actually, so it is important to keep in mind these relations. Let's focus on it more. As I just mentioned, it is quite important to know these relations. If your ultimate strength is below this value, you'll have to use this relation for your endurance limits. But what does it mean? If in a problem you have SUC equal to 100 megapascals, it means that you are below this range. So your SE prime will be equal to the half of this value, and that is 50 megapascals. Cool. So what if you're not in this range? Well, simply you'll use these relations. Okay, apart from SE, we need to know other things about this diagram. If you are an engineer or an engineering student, you'll have to study this diagram to design a component which works permanently or has a good application. Well, first of all, we have two different areas, high cycle and low cycle. I just told you a brief introduction to low cycle and high cycle, but each of them has their own information, has their own relations. For the low cycle fatigue, which is basically between 1 till this value, and it would be this part of the diagram, we have an important relation, and that is SF, the fatigue strength, will be equal to SUT times N divided by 3. We have this parameter F here. We will discuss it later. And for the high cycle fatigue, the number of cycles will be here. Actually, this part of the diagram. And the relations are SF equal to A times N powered by B. But what is A and what is B? Don't worry, A is defined as these are our two relations that consist of F. So F seems to be an important factor since it has been used in many places. But you don't need to worry about this one because it is simply obtained. If you are willing to obtain F, you can use this diagram. This diagram is available in all engineering handbooks, so it shouldn't be your concern. This diagram has the y-axis known as F, the x-axis known as SUT, and as an example, with having this SUT, you can find the value of F. Pretty easy. Now let's discuss about Marin factors. What are these factors? Well, there is something you need to know about SE prime. SE prime, which I just mentioned, is the endurance limit. But which kind of endurance limit? The one in experiments, or in laboratories, or the one in real cases? This SE prime is the one obtained from experiments in a laboratory. It is pretty accurate with no certain errors. But the one we have in real cases is not this easy. We have to define some factors in order to modify this SE prime, in order to obtain something more realistic, in order to solve our problems better. So, we have to define Marin factors. There are 6 factors here. The multiplication of these numbers will give us the real SE. So we have to define different factors: Ka, Kb, Kc, Kd, Ke, and Kf. Each of them has their own definition and own application. We start with Ka. Ka is a surface condition modification factor. In fact, the SE prime obtained in the laboratory is from a very perfect polished surface, but the one we have in real cases is not like this. It could be ground or anything else. So we need to apply the Ka factor to obtain something more realistic. The other factor is Kb, the size modification factor, something that depends on the cross-section area. Is it circular or something else? The other one is the load modification factor. If you remember from the previous slides, I mentioned that the SN diagram is obtained from a test called the rotating beam test. The rotating beam test was subjected to a constant bending load. But in real cases, it is not just a bending case. It could be a torque or an axial force or anything else, or even a combination of them. So the load modification factor will give us a real approach. The other one is a temperature modification factor. This one totally depends on the temperature you are working with. The other one is a reliability factor. This is not an important one, and it is always given in the question. It has also some relations that we will discuss later, but for now you just have to know that the reliability factor is commonly something for the reliability, for knowing how accurate or how perfect your component is. There is another one called Kf, and the last one actually. The last one is not really important and it is not really used in problems, but if you ever see something like this, you don't need to worry about it because it is commonly given in the question. You might be wondering how to apply all of these factors at the same time, but you don't need to worry because we will solve an example and it will help you much better. Thanks for watching us. Don't forget to check other videos for better information about fatigue failure.